Hi everyone, today I'm going to talk about a drawdown paper from Chevron. Drawdown management is a pet project of mine. Maybe one day I'll talk about my thesis on YouTube, but we'll save that for another day. This paper will cover some of the strategies and the workflows that are required for effective drawdown management. I really hope you enjoy the video. Make sure you subscribe and click on the notification bell. That way you get your notifications every Sunday as I upload every Sunday. And yes, I have a cat right behind me. Well, like I've mentioned before, I hope you enjoy the video.
As I mentioned in my introductory video, I'm going to talk about drawdown management optimization from a time-lapse numerical simulation. This is written by Pablo Agustin Crespo and Sergio Cuervo from Chevron. I gave some background information. This is to provide some context between drawdown and choke management strategies, and then I bolded the objective. Their modern production practices have migrated from a choke to drawdown management strategies to improve control on the effective net stress over the proppant, and that's avoiding hydraulic fracture and conductivity damage. The paper introduces a workflow using a non-coupled numerical simulator with the addition of time steps of one-way coupled calculations. The paper also mentions good production strategies that should consider. They would avoid hydraulic fracture conductivity damage due to proppant crushing, embedment, formation spalling, or formation fines migration. You want to avoid matrix perm reduction by rock compaction or natural microfractures collapse, and of course, economics optimization. I mentioned this before about choke management versus drawdown management and how production practices are now transitioning to drawdown management. I want to just clarify what the differences are because sometimes these words are used interchangeably in the industry. For choke management, it's choke defined as a function of time. It's strongly dependent on lateral length, number of stages, and fluid type. There's no pressure data required and only requires production engineers to be aware of choke management schedules. For drawdown management, choke is defined as a function of flowing pressure. It's independent on lateral length, number of stages, and fluid type. It requires wellhead flowing pressures, preferably flowing bottom hole pressure, and it requires follow-up from a reservoir and production engineers. I wrote down what they have expressed in the geomechanics portion. Usually, if you have a coupled geomechanics simulator with numerical simulation, and if you do this the formal way for calculations, it takes quite a bit of time. So the paper gives you analytical approximations, and they provide two essential equations or two assumptions. So the hydraulic fracture behavior is a function of minimum horizontal stress minus the flowing bottom hole pressure. And during the depletion, the changes in effective net stress will close the hydraulic fracture and reduce conductivity. It's the proppant grain that will provide the resistance, and that resistance won't occur if embedment happens. The paper also gives a workflow of what data is needed in order to put this in your non-coupled numerical simulation. For instance, you need to import log data and set up wells with your well survey, microseismic completions, and production data. You need to build your structural model with bore site images, formation tops, pilot integration, seismic and DFM creation. Then you need to define the hydraulic fracture treatment with fluid, proppant, treatment path, perfs, talk to your completions advisor, and finally your treatment data. You generate hydraulic fractures by honoring the treatment of microseismic and proppant transport and stress shadowing. And then you go to your production simulation where you use your unstructured grid, you input your zone properties, you get a proper history match and production forecast, you get your NPV calculations for your drawdown optimization, and then you run sensitivities. Once you get a proper history match, the paper talks about how you can get your pore pressure calculations from your simulated rock volume, and you use that first equation that I talked about in inputting your pore pressure to get your minimum effective stress in your SRV. Next, the paper talks about drawdown management optimizations, where they quantify what exactly is a conservative, moderate, aggressive, and very aggressive strategy. A conservative strategy is between 0.5 to 1 psi per hour. A moderate strategy is 1 to 2.5 psi per hour. An aggressive strategy is 2.5 to 5 psi per hour, and a very aggressive strategy is 5 to 10 psi per hour. One thing to note in this chart is that the effective net stress peak in each of these strategies are different from each scenario. And the paper also makes sure what is an optimal drawdown strategy with other tests. So they check with prop and long-term conductivity tests and prop and embedment tests to see which strategy would minimize conductivity damage. Additional considerations that the paper talks about in developing this innovative workflow is that effective net stress over hydraulic fracturing is not uniform along the hydraulic fracture network, and the depletion change is driven by geomechanics, for example, Poisson's ratio. Pinch point areas are not considered in the modeling, but they can contribute to conductivity reduction, and that could close off the hydraulic fracturing network. Finally, minimum horizontal stress was a simplification for this workflow, but the whole stress tensor should be included in conventionals, especially when there's a non-planar hydraulic fracture network. And that concludes the presentation. Be sure to follow me on Instagram, Facebook, LinkedIn, and Twitter. My handles are Yogashri Pradhan for all of them. So I'm quite easy to find, and my handles are pretty consistent. I really appreciate you taking the time and watching this video, and hope these salient points give you an idea of what this paper is about. I'll be sure to talk about more papers in upcoming videos weekly.